Great. So to start this talk, just a little bit about Ting. So Ting is a Genentech endowed assistant professor in the biostatistics department at the University of Washington. She received her PhD in statistics in 2019 from the University of Wisconsin-Madison and spent 2 years as a postdoctoral fellow in the statistics at the Wharton School of University of Pennsylvania. Her current research focuses on variant adjustment in randomized controlled trials, Mendelian randomizations, and other natural experiment methods for causal inference. So today, I think we'll talk to us about difference in differences. You have about 50 minutes for the talk, and I'll let you know 5 minutes before the end. If anyone has questions in the audience, please raise your hands. Same for Zoom people, and I'll call it out. Okay.
Sounds great. Thank you so much, Emma, for the nice introduction, and thank you so much for the invitation. I'm very happy to talk here today about a work that we did in the difference in differences. And it's great to be here to see old friends and new friends. And so for this talk, if you're interested to look at the slides later, you can download the slides on my website, or the slides are there. So it's a negative correlation strategy for bracketing indifference in differences, which is an extension of DID. First, I would like to acknowledge that this is a joint work with my postdoc advisor, Dr. Dylan Small, and Luke Keel in UPenn, and also Raiden Hasegawa in the Google. So first of all, I would like to start with this motivating example of strict voter ID loss. Actually, we have another application, but I think this application is more interesting because it's all over the New York Times and other news outlets these days. So this strict voter ID loss is a law that requires voters to present a valid photo ID in order to cast a vote. So between 2004 and 2008, Georgia and Indiana, these two states, they first passed the strict voter ID laws. And for example, Georgia would require a valid photo ID in order to vote. If a voter cannot present a valid ID, they are allowed to cast a provisional ballot, and for that ballot to be counted, they need to return within 3 days to present ID. And for Indiana, the details are slightly different, but they are all categorized as the strict voter ID laws. So the strict voter ID laws have been under a lot of debates. And so essentially at the core of this debate is a balancing of election security and also the ease of voting. And opponents of the strict voter ID laws, they argue that these laws place disproportionate burden on the low-income voters, minorities, and young and elderly. And so empirical studies also have reported mixed findings. And with the more and more strict voter ID laws being passed, it's crucial to understand whether these laws will affect voter turnout. But it's actually quite hard to evaluate the strict voter ID laws on voter turnout. There are many reasons, and the crucial one is that this state, they adopt strict voter ID laws in a highly purposeful fashion. And so therefore the states with and without these laws, they're systematically different, which may be different in a way that relates to voter turnout. And to see this is not merely theoretical, you can see in this figure that the turnout rate in 2000, which is before any state had adopted strict voter ID laws, the states that would eventually adopt strict voter ID laws by 2015 actually has about 3% lower the voter turnout rate compared to the other states. So they have systematic difference, and it's important to address them. And if these differences do not vary over time, then difference in differences is a method that's sufficient to address for them. So the different diff, DID, is commonly used for estimating causal effects in this type of settings. And the prototypical DID application is to address how do state policies affect individuals. For example, do Missouri handgun purchasing licensing law affect firearm homicide rates? And did minimum wage laws change employment levels? And for example, in this motivating application, this strict voter ID loss changed turnout rate. So I'll give a very basic introduction of the DID for causal effects. In the most basic setting, we will have a pre-treatment period and a post-treatment period denoted by T equals 1 and 2. So we will have a treated state that initiate the treatment during this 2 period. So we will have the outcome before the treatment initiation and outcome after the treatment initiation. So this black line represents the observed outcome path for the treated group. And the treatment effect of interest is usually the treatment effect for the treated group in the post-treatment period. So what we actually want to conceptualize is a counterfactual outcome path for the treated group had they not taken the treatment. So this is represented as this gray dashed line, which is the counterfactual outcome path for the treated group in the absence of the treatment. And then their difference in the post-treatment period will be the treatment effect of interest. And of course, this is a counterfactual question because we don't get to observe the outcome path for the treated group in absence of the treatment. So in this talk, the identification will basically means expressing quantities of interest using observed variables. And in this case, because the black dot is the observed outcome for the treated group, so identifying the treatment effect is essentially equivalent to identifying the counterfactual, the gray dot. So the DID works by identifying a control group which satisfy this parallel trends assumption, which says that in the absence of the treatment, the treated group and the control group would evolve over time in the same way. And under this assumption, we can basically take the observed outcome path for the control group and use that to recover what would have happened for the treated group in absence of the treatment. And then their difference will, and then we can calculate the difference for the treated group and the pre and post difference for the control group. And then their difference, which is the difference in differences, will be equal to the treatment effect. And alternatively, you can use this linear model, which include the time effect and the group effect, and also an interaction term. Then the coefficient will be the DID. But in many cases, the parallel trends assumption may not be plausible due to state-specific events. For example, in the voter ID case, if the treated group was targeted by both major party campaign in the post-treatment period, then this treated group in the absence of the voter ID law will have higher turnout than this control group because of this campaign. Then this DID using this control group will overestimate the treatment effect because the control group is having too flat trend compared to the treated group in the absence of the treatment. And there are many methods proposed to address this violation of parallel trends assumption. And here I will briefly highlight 2 of them. So the first method is asking what's the worst case violation. So basically we need to specify a delta which bound the violation. So if we know the violation is non-negative and it's upper bounded by delta, then we would know that the treatment effect is actually bounded by DID minus delta and DID. And in this case, even with infinite sample, we still cannot exactly know the treatment effect, but we have a meaningful bound for the treatment effect. So this is called partial or set identification. And this is in contrast to point identification. So the downside of this approach is that we need to specify a delta, which you may not have the domain knowledge to specify that. And another approach is by this Hasegawa, Webster, and Small paper in 2019. And their idea is to propose using another control group that has too steep trend. So we will have a control group with too steep trend, which will lead to underestimate of the treatment effects, and a control group B with too flat trend, which will overestimate the treatment effect. And then we just apply DID twice. And then these 2 DID parameters will bound the treatment effect. So in this case, we don't need this delta parameter because we use more information from another control group. And we know these two control group, they will bound the counterfactual outcome path for the treated group without the treatment. So this is still a partial identification strategy because even with infinite sample, we don't know exactly the treatment effect. And again, because the identification of the treatment effect is equivalent to identification of the counterfactual. So in this case, this gray region is actually the identified set for the counterfactual outcome for the treated in the post-treatment period. Then basically in the rest of the talk, I will focusing on the partial identification of the counterfactual outcome for the treated group. So in our work, our motivation is really the multiple time points. So the data are available not just for 2 time points, available for multiple post-treatment time periods. And we are also interested in how the treatment effect changes over time, such as in the voter ID example, people hypothesize that the strict voter ID law initial effect may be different from their long-term effect. And in this work, we propose a framework for more flexible DID analysis, which will propose strategy for partial identification of the treatment effect under a monotone trend assumption. And for this part of the talk, I'll be very non-technical. And then in the second part of the talk, I will demonstrate that because this partial identified region has a very specific form, so it creates inferential challenge. And so we propose a novel bootstrap inference for that. And this part, I'll be a little bit, I'll be more technical and propose some interesting statistical questions for you to consider. And finally, I will talk about the application to the voter ID example. Right. So first, what is the monotone trend assumption? With multiple time points, we still use t equals 1 to denote the pre-treatment period and t equals 2 and afterwards to denote the post-treatment period. And then we have this black solid line to represent the observed outcome path for the treated group. And then we use this dashed gray line to represent the counterfactual outcome path for the treated group without the treatment. So essentially, because we mentioned that we just need to identify the counterfactual outcome path, so we will be omitting the observed outcome path for now. And we still have 2 control groups, control group A and B, and they will satisfy this monotone trend assumption. So first of all, some notations here. We use this delta TG to denote the change in outcome from t-1 to time t for group G. So for example, this delta 2b actually denotes the changing outcome for control group B from time 1 to time 2. And similarly, we have this delta 2a for the changing outcome for control group A. And we also have this notation for the change in the potential changing outcome for the treated group in the absence of the treatment, denoted by delta 2 0 treated. So the superscript 0 denote that this is a counterfactual quantity. So the monotone trend assumption says that this changing outcome for these 2 control group, they will bound the changing outcome for the treated group. So specifically in this case, the delta 2b provides the upper bound and delta 2a provides the lower bound. And this needs to be held for every 2 adjacent time points, but which group provides upper bound and which provides a lower bound is allowed to switch over time. So in summary, this monotone trend assumption is stated as this. So the minimum of these adjacent time points changing outcome for the 2 control group provides the lower bound and the maximum provides the upper bound. So this assumption can be related to some existing models that people use. For example, the parallel trends assumption will assume that the changing outcome for every group and also for the counterfactual treated group will be equal. So this is included in our framework as a special case. And the second and most important model that we can connect to is the interactive fixed effect model that's commonly used, which includes a time effect theta t and the group effect eta g, and also a group specific term lambda g interact with a latent time varying factor ft. So in this case, if we have two groups, two control groups, lambda A and lambda B and lambda treated, if they are ordered, then we know that they satisfy this monotone trends assumption. And this actually has an interesting application, which is if we conceptualize this FT as the business cycle, which can fluctuate over time. And if we're interested in how the minimum wage policy affect the employment level, then we can take two industries. One is counter-cyclical, one is cyclic to the business cycle. Then these two will provide bound for the counterfactual treated group. So the you can, so the monotone means like different groups, they are monotone, but not monotone in time. So like the delta T A and delta T B, they should and delta T treated. Yes. Yes. Yeah. Yeah, I can change the name. Yeah. 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 Yeah, maybe like bounded trends assumption or something. Sounds good. Yeah, it's still under revision anyway, so I've got time to change it. So this is the interactive fixed effect model, and this model is it includes the parallel trends, also includes parallel trends model as a special case, and we find this interactive fixed effect model actually is very helpful to motivate the selection of the control group based on domain knowledge. And this monotone trends assumption, maybe another name, is also related to the parallel growth assumption and changes in changes model, but the details are omitted in this talk. They are specified in the paper. So I'll give an example of how do we select the control group. This example is based on the domain knowledge and this interactive fixed effect model. So this is to study the effect of minimum wage on the employment level. And using the standard DID design, you will choose a treated group and then a control group that satisfy the parallel trends assumption. However, the parallel trends assumption can be violated because these macroeconomic shocks can have differential effects on different economic sectors, for example, different industries. And then basically in the absence of any policy, you may have different industries not following parallel trends assumption. So in this case, basically, if we are interested in the minimum wage on this federal government and domestic service industry, then we can, based on economic theory, we know this is modestly positively correlated with the business cycle. Then we can basically find two control industries. One is strongly positively correlated with the business cycle, like the construction. And then another industry, including the hospitals, nursing homes, and agriculture, which are known to be negatively correlated with the business cycle. Then based on this interactive fixed effect model, we know that they are lambda A, lambda B, and lambda treated, they are ordered. Then we know these two control groups will bound the counterfactual outcome path for the treated group. It is not time series. Yeah, it's the basically longitudinal data, like panel data. Yeah, and then a second example that we have considered recently is the effect of income support programs on the drug overdose death. And in this case, if basically the standard DID will basically to try to find a control group that satisfy the parallel trends assumption to the treated state. However, they may not satisfy the parallel trends assumption because one major concern is that the US fentanyl supply can have differential effects on states. And some states were hit harder while some states are relatively insulated from the fentanyl. So in this case, if we are interested in these several states, that were hit modestly by the US fentanyl supply, and we think the US fentanyl supply is a latent time varying factor, then we can find two control groups. One is strongly positively affected by the fentanyl, and one is not much affected by the US fentanyl supply. And then these two control groups will be able to satisfy our assumption. Of course, you can think, okay, I measure this US fentanyl supply, I can adjust for it, but there are also a lot of problems with this measurement. So if you think these measurements are problematic, but it's useful for selecting these control groups, then our method may be more preferable. Okay, so in other situations, we may not have enough domain knowledge to select these control groups. Then we propose a data-driven approach, which try to find some pattern that satisfy our assumption. So in this case, we propose a very simple lemma, which basically relates the monotone trend assumption to the negative correlation. So essentially, we have this gamma Tg to denote the relative outcome difference for the treated group and the control group. So you can see in the bottom figure that the gamma 1A is the relative outcome for control group A relative to the treated group. And then the gamma 1B is similarly for the control group B. And then to see why this is a negative correlation, we basically can subtract the outcome for the treated group. And then we do this for every time point. And then you can see that when the relative outcome for control group A increase, then the relative outcome for control group B must decrease. So if one is increased, one must be decreased. So we call this a negative correlation between the relative outcomes. Concordant? Yeah. Okay, I'll look into this and maybe think of better names. So this is so we, based on this, this motivate a control group selection approach that's data driven. So first of all, we need to identify candidate control groups, control units that were never treated during the study period. And then we use a prior study periods to select the control groups in order to avoid using data twice. So this is not perfect because the prior study period is usually also correlated with the study period because it's longitudinal measurements for the same units, but this at least mitigates the concern. And then we just calculate the relative outcome for every every candidate control unit, and then you can apply the your favorite hierarchical clustering algorithm to find two clusters of the control units that have strong negative correlation. And then in this case, we can use them as the two control groups. So this is motivated from these relative outcomes. Like when one is increased, the other must be decreased. So they have this negative correlation structure. So under these assumptions, now we have covered our key assumption and how we motivate how these connect to existing methods and how to select the control groups. Then we can bound the counterfactual outcome path for the treated group based on these two control groups satisfying the monotone trend assumption. So with 2 time points, it's easy. We mentioned that this gray area actually bound the counterfactual outcome for the for point 1 to point 2. And then for the second period, actually this is infeasible because we don't know the starting gray dot because that is unidentifiable. So essentially under our assumption, we need to consider the worst case scenario by moving this gray dot to their boundary. And then this expanded gray area is the partially identified set for the counterfactual outcome path in the absence of the treatment. And then we do this for every time point. You can see that the uncertainty of the counterfactual outcome actually propagate over time. So you can see this gray area expand larger and larger. So some people may wonder, this is very conservative if you want to study the post-treatment periods long after the start of the treatment, we agree. So there are more work that can be done to propose like stronger assumptions that are more that are also reasonable and to get more informative inference. So in this case, we have this gray area to denote the counterfactual, the identified set for the counterfactual outcome for the treated group. And then we just compare it to the observed outcome path for the treated group. And this will give us the partially identified region for the treatment effect. So specifically, we can calculate DID for every 2 adjacent time points for the 2 control groups. And then for time point 2, we just take the maximum as the upper bound and the minimum as the lower bound for the treatment effect. But for time point 3, basically we need to take the sum of the pairwise maximums as the upper bound and the sum of the pairwise minimum as the lower bound. And similarly, for any general time point t, we just take the maximum of the 2 DID, the pairwise maximum and the pairwise minimum as the upper bound and lower bound. So this will be our partially identified result. So under the monotone trends assumption, the average treatment effect for treated at time t will be partially identified via these bounds, where the lower end is the sum of the pairwise minimum and upper end is the sum of the pairwise maximum. Yes, here there's no randomness yet, so it's all like in the population setting. Okay, so yes, we have like in the inference result, we will talk about the randomness. Yeah. So in this case, so because our assumption covers the parallel trends assumption as a special case, you can see that when the parallel trends assumption holds, then the DID for group A and DID for group B will be equal. And then you can see that this partially identified region will just shrink to a single point. So it will automatically go back to the same identified result if the parallel trends assumption hold. And so in the next slide, I will talk about the inference, but in order to prepare for the inference section, basically we noticed that the identified set can be equivalently written as this, so this minimum of all the possible combinations and the maximum of all the possible combinations. So for example, when t equals 3, the lower end will be the minimum of all 4 different parameters, which are all the possible combinations for the sum. And then we basically, in general, so we summarize this inference problem as that we have a set of bounding parameters denoted by theta t. And so this will contain 2 to the t minus 1 elements, which we consider finite many. And then for notational simplicity, we will omit the t. So essentially, the goal is to construct confidence intervals for the identified set where the lower end is minimum of a set of parameters and the upper end is the maximum of a set of parameters. So we call this union bounds because it's like a union of different intervals. And we are also interested in the confidence interval for the parameter of interest, ATT, which falls in this identified set. So the difference between inference for the identified set and for a parameter that falls in the identified set. So there's quite subtle but important difference. It's covered in this very famous paper, Imbens and Mansky 2004, and this Stoy paper 2009. So in our case, the challenge is essentially in the minimum and maximum operators, because the simple sample analogs, if you calculate the minimum of the theta j hat, will be biased if there's no single parameter achieve the minimum and maximum. And the canonical bootstrap is also inconsistent. There's no model. So we just have like some parameters theta j, and then we know based on our previous assumption that the minimum and the maximum, they provide the bounds. So it's like non-parametric. So we just translate the problem into inference of this minimum and maximum identified set. And next, we will basically have regular estimators for every theta j, and then based on them to construct a confidence interval for this identified set and the ATT. Yes, so this slide is highly is very general. So you can imagine that you just have a bunch of theta j hat, and then you want to do inference on this minimum and maximum interval based on those theta j hat. No, not this way, but so for example, if the parallel trends assumption hold, then basically all this theta j will be equal to the treatment effect, right?
Because theta j is sort of like a part of the signal, so it is like a fixed value. Right?
Mm-hmm.
But our observed data is always small.
Yeah.
Always have some randomness.
Yeah.
And my question is how to model the randomness.
Yes. Yeah.
So like a sequence model at some frequency to sequence theta j.
Yeah, basically, like we assume IID assumption. So essentially, for example, when we have let's say we have for t equals 3, then the theta j, theta 1 to theta 4 will be these 4 parameters, and then the theta 1 will be DID 2a plus DID 3a, and then the DID 2a. So it's a parameter, which is the difference in differences in expectation. Then we just use their sample analog, use the sample version of this difference in differences, which will estimate this DID 2a plus DID 3a. So we assume these y's are IID essentially. The y is the outcome. Yeah.
Yeah, y's are IID. But each y is a long sequence.
So basically the y basically is for every state's outcome. Then we assume the outcome for the between states are independent and identically distributed, but within state there could be correlation. Yes.
So this correlation like the temporal correlation.
Yes. Yeah. Yeah. So yeah, thanks for the question. So basically, this is the statistical problem that I want to bring to your attention, that it's the minimum of a bunch of parameters, and you might have regular estimators for each of these parameters. But essentially, your parameter of interest is the minimum and the maximum of theta j. So basically, there are two common existing approaches which can be overly conservative. So the first one is this intersection union method. It's very simple. You just take the lower confidence interval for every theta j, and then you take the minimum. And by standard argument, you know that this covers the minimum of theta j. But this can be, you can imagine this can be very conservative if the theta j's are equal to each other. Then you have this minimum of theta j's being biased downwards. So the other option is the standard percentile bootstrap. Basically, you generate bootstrap sample for each one of them. You calculate the bootstrap analog of the theta j, and then you take the minimum, and then you do this many times and do the alpha over 2 quantile. So by a generalized max-min inequality, you would know that this standard percentile bootstrap is even more conservative than the intersection union bounds. So these two are very conservative. So our proposal, in order to construct a valid inference but less conservative, is to do also a bootstrap inference, but with a slightly different structure. That looks like this. I'll explain this in the next slide. But essentially, this interval is similar. It is asymptotically the same as the standard percentile bootstrap without the minimum and maximum operators. But with this minimum and maximum, they will be less conservative. Yes, please. Oh, yeah, sorry. Yeah, should be max. Yeah. Okay. So the intuition of here's a slide that demonstrates the intuition of the bootstrap approach that we propose. Basically, let's consider the lower end as an example. We use the LX to denote the true distribution of the minimum theta j hat minus the minimum of theta j multiplied by root n. And then the L hat x be the bootstrap estimate of LX. And then when the theta j's do not have a unique minimum, then L hat does not consistently estimate LX. But interestingly, there is a directional inconsistency. As we can show here that actually the bootstrap estimate L hat x will underestimate LX, which means if we, based on this bootstrap estimate and use the 1 minus alpha over 2 quantile, which guarantees that the area under this orange curve is larger than 1 minus alpha over t, then by this directional inconsistency, we know that this area under LX is even larger than 1 minus alpha over t. So this justifies the validity of our bootstrap procedure. A little bit formula at the bottom here that we find this quantile based on the bootstrap estimate. And then based on this conditional inconsistency, we know that the L of this quantile is also larger than 1 minus alpha over 2. And then based on the definition of this LX, you can reorganize the terms a little bit. Then you know that this minimum theta j hat minus the 1 over square root n, the quantile is smaller than the minimum of theta j with high probability, which justifies why we can use this as the lower confidence interval end. Then we basically reformulate this a little bit because the minimum of theta j hat is fixed for each bootstrap iteration. Then this gives us like 2 minimum theta j hat minus these quantiles. All right, so then we have a formal statistical statement for the bootstrap inference procedure. It's a bit busy slide, but essentially we have these LX being the true distribution and L hat x be the bootstrap estimate, and we define this Rx and R hat x with minimum replaced by maximum. So under standard assumption on the bootstrap consistency, which essentially assume ID with finite second moment, and these theta j, they are a function of the sample averages, and this function is continuously differentiable at mu with non-zero derivative. Then we can show that the for any value of x, so the supreme of x, the L hat x is smaller than Lx. And then for the R's, basically the R hat x will overestimate the Rx, so we can use them for the inference. So part B basically justifies that the confidence interval we use covers the identified set with high probability. So what about part C? So for part C, the idea is that because we want to construct confidence interval for the treatment effect, which is a parameter within the identified set, actually we can do better. The rationale is that if the identified set is wide enough compared to the measurement error, then you know that the treatment, the parameter within this set can only be close to one side of this boundary. This means that the probability of not covering the parameter is only one-sided, because the other side must be negligible because the width is much larger than the measurement error. So in this case, if the width of the identified set is large enough, then you only need to consider 1 minus alpha critical value, because the the probability of non-coverage is only one-sided essentially. So that's why we can improve for the confidence interval for the treatment for the identified parameter. And then this shows that the regardless of the position of this identified parameter and regardless of the length of the identified set, that we have the correct coverage probability. It's not correct, it's conservative. Yeah, it would be great if we can do correct. So some remarks on the last point is that the last point is a little bit complex, but the idea is that we can use the critical value of we can use the significance level 1 minus alpha when the bounds are wide enough, in the sense that rho multiplied by the width, it goes to a non-zero constant. And if the bounds are not wide enough, then we still need to use 1 minus alpha over 2 significance level. So this rho, we have a we have a choice of rho in the paper. So rho is in the order of the root n over log n, and then we can use that rho to construct the p hat in order for constructing the confidence interval. So when the parallel trends hold, again, our confidence interval is similar to that from the standard DID. It's not that conservative. We can see that from the simulation, and when the monotone trends hold, but the parallel trends is violated, our confidence interval will be valid, but the from the standard DID is not. So the previous theorem also provides half median unbiased estimators for the bounds. Basically, we have this minimum of theta j hat minus this term being a half median unbiased, in the sense that this estimator will be smaller than the minimum of theta j with more than 50% of the probability. So this can be shown based on the previous result. So the last point I want to mention that is actually much more challenging to obtain uniformly valid confidence interval for this minimum and maximum thing. In the sense that if we want to have the coverage taking an infimum of all the possible distribution within a distribution class, then this guarantee is much stronger, and it's much more difficult to construct a procedure that satisfies this. And in our paper, we propose a procedure that uses a subsampling idea, but it's not very informative. So it's quite challenging in this case to provide uniformly valid confidence interval. But I should say the intersection union bound is valid, but it can be very conservative still. So, yes.
How is this? Is this related to this to the precision correct?
Yeah, it's so. Their connection. So in their case, that's a great question. In their case, they are interested in the intersection bounds, where the identified set is maximum of theta j in the lower end and some minimum of other set of parameters in the upper end. So that's a different problem. But this correction of the so this part C of adjusting this significance level is similar. Okay, so I will quickly demonstrate the simulation of the bootstrap procedure. So consider two cases where case 1 is satisfied, the parallel trend, which is point identification, and the case 2 is partially parallel trends where but satisfy our monotone trends assumption. Then you can look at the intersection union confidence interval in the percentile bootstrap. You can see that the percentile bootstrap is more conservative than the intersection union bounds. So the intersection union bounds is quite conservative in the case when the parallel trend assumption holds. So a lot of the parameters are equal to each other, and there are a lot of them. So it creates like much conservativeness. However, in our case, for our procedure, we have like less conservative, like shorter confidence interval still with more than 95% coverage probability. And the version for the point identification, because we can adjust the significance level. So this is especially in case 2, it's like shorter compared to the version for the identified set. And lastly, this is our half median unbiased estimators, and you can see that it's less biased compared to the simple sample analogs.
If I put it seems to me like you look at the last 3 rows, the rest of the placebo is actually quicker than the
Yes, a little bit, yeah. So I mean, in this case, the so the intersection union bound is not that conservative because a lot of the parameters are not equal to each other. So in this case, it's not bad. So you can imagine if you have a unique minimum and a unique maximum, then the intersection union bounds in some conditions are actually correct with the correct coverage.
Please save the rest of the question for the interest of time.
Yeah. Okay, so I will be quick on this application. So this is the last part of my slide. So basically, we want to apply our method to the strict voter ID laws on voter turnout. And in this case, the treated states are the Georgia and Indiana, and the pre-treatment period is 2004, post is 2008 and 2012. And so the goal is to bound the effect of strict voter ID laws on overall voter turnout in these 2 states in 2008 and 2012. So we have 2 steps. The first step is to construct and validate the control group selection, and step 2 is to estimate inference of the treatment effect. So let's take the Georgia as an example. We construct the control group using some pre-period data, so 1980 to 2000, before 2004 and 2012, which is the study period, using the data from the United States Elections Project. And the candidate control units are the states without strict voter ID laws by 2012. And then we calculate the correlation for each pair of the candidate control units relative outcomes, and then we apply the hierarchical clustering to find two control groups that are negatively correlated. And the second is to validate the control group selection. So we still focus this same time period, but use turnout data from the CPS voting supplement, which is a different data source compared to the US election projects. So we want to validate that our control group selection indeed satisfy our assumption. So the clustering algorithm looks like, the results look like this. So we select the control group A, include the Oregon, Michigan, Iowa, and control group B include Wyoming. And you can see that the relative outcome for the Wyoming is indeed quite negatively correlated with this other control group. But the downside of this procedure is that outside this interactive fixed effect model, it's really hard to justify why they are negatively correlated. So we do a validation using the CPS data, which we plot the turnout rate for the control groups and how that varies over year. So we do the relative outcomes, which is easier to see. Then you can see that when one group increases, the other group must decrease. So this satisfies our assumption. And we also propose a falsification test, which is similar to the standard DID's parallel trends test used the pre-period. So it's a falsification test. Not rejecting the null doesn't mean the assumption is violated, but rejecting null do demonstrate some evidence of violation. So in this case, we find no evidence of violation. So let's move to the second step of constructing an inference of the treatment effect. So we focus on the 2004 to 2012, and then this is non-overlapping with the data in step 1 to avoid, mitigate the concern of using data twice. And then we can see that for the 2 control groups, their turnout actually decrease over this period, but for the treated group, it's actually have this increase. So basically using our identified approach, then we know that this gray area is the partially identified region for the treated group in the absence of the treatment, then you can see compared to this gray region, this observed outcome path has a big increase, which intuitively, which visually demonstrate the turnout is actually increased. So we can do the estimation bootstrap, and essentially the results is like this. So based on the DID analysis, we have a version of the unadjusted and the adjusted for covariance version, and you can see using either method that the causal effect of the voter ID law on turnout is positive, and similarly for the standard DID method. So in the conclusion is that the strict voter ID laws actually increased the turnout for Georgia in 2008 and 2012, larger than 2.5% adjusted or unadjusted. And the confidence intervals from the DID bracket are slightly wider than that from the standard DID. This is due to the uncertainty that in whether the parallel trends assumption holds or not. Okay. So similarly for Indiana, so we see that the voter ID laws actually also increased the turnout in 2008, but no evidence in 2012. Using the standard DID, they find evidence that the voter ID law increased the turnout rate for Indiana in both 2008 and 2012. So you may be curious why the strict voter ID laws are actually not lower the voter turnout. So in fact, our result is consistent with many existing works, and there are three major hypotheses or explanations for this phenomenon. So the first one is there is a lot of counter mobilization strategies to this voter ID law. So a lot of the groups are organized to make sure people are aware of these voter ID law restrictions, and also to help them to get the voter ID. So this help to mitigate the inconvenience of needing the voter ID. And the second is there is, so because of the discussion during that time on the public media, so it triggers anger for those who thought they were like, they were disadvantaged by this law. So it actually motivate them to vote. And the third reason is that the law may increase the confidence in people's more confidence in the voting in the voting fairness, and this may lead to more people vote. But we need to still recognize that people without valid photo ID law do face a higher barrier to voting. So in summary, we propose a framework for more flexible DID analysis without the parallel trends assumption. So we have an identification strategy under the monotone trends assumption. This can provide a partially identified set for the treatment effect. And because the partially identified set has this minimum maximum operators, so we propose a bootstrap inference with statistical guarantee. And we have approaches for control group selection and sensitivity analysis and falsification tests, which are not discussed in detail in this talk, but I have appendix slide. If you're interested, you can look at them. And this is the reference for our paper. It's been unbelievably long to publish this paper. So we have an R package on GitHub. Thank you so much for the attention.
Thanks, Ting. So we do actually have some time for questions. Okay?
Thank you.
Not my area, but I wondered if there's like an intuitive way that you could describe the rationale behind why it's important that the two control groups have that negative correlation. If the graphing made sense to me, that you're trying to find the worst and best case scenario, but is there any non-equation sort of explanation for the negative correlation?
Yeah. So so the reason we need two control groups is because we want them to bound the counterfactual outcome path for the treated in the absence of the treatment. And why they satisfy this relationship, it's so one intuitive way to understand is like, for example, in the economic example, like the how different if I use two industries as the control group, and then another industry as the treated group. Then because they fluctuate with the business cycle, and some are very strongly correlated with the business cycle, some are negatively correlated, then you can imagine that they will bound a group that's like modestly correlated with the business cycle. Yeah, so this is the rationale, like why these two groups satisfy the assumption. And then because of this assumption is the nature of this assumption, so the worst case actually becomes wider and wider. Thanks.